Alright, so I'll do another example of how to do it from regular coordinates to cylindrical. So pretty much they're given as this, so -3 to 3, 0 to 9 minus x squared, square root 9 minus x squared, and 0 to 9 minus x squared minus y squared. Our function is x squared plus y squared, dz, dy, dx. Now they want us to change into cylindrical. So I think this was an easier example than the first one up there. So pretty much you have to look at the bounds again. So let's not worry about the function. So I made a mistake. I'll fix this in a few, but so if we look at the bounds, it says 0 to 9 minus x squared minus y squared, and this is z. We're looking at z. So if we look at this whole thing, is with respect to z. So if we write that z equals 9 minus x squared minus y squared, right? We get that equation. So now, same thing like we did in the other problem. We have negative x squared minus y squared. So we have z equals 9 minus r squared. I think this is a shortcut, so you don't have to draw it out in 3D. It's like when you have the z bound, all you just have to do is like replace your x and y's with pretty much like the r cosine r sine. But in this case, if you like do that, you'll end up with 9 minus r squared. So pretty much what I did like a little shortcut. So instead of like replacing like x with r cosine and then squaring that and then y with sine and squaring that, I just wrote, like, I know r squared equals x squared plus y squared, so I just wrote 9 minus r squared. So pretty much that's going to be my z bound. So 0 to 9 minus r squared. I made a little mistake here, but I'll fix it in a few. Even here, even if we look at the function, we have x squared plus y squared equals r squared. So here we can replace this with r squared. That's what my mistake was. Now if we look at the second integral, so our y bounds, so it says 0 to 9 minus x squared. This is a little bit simpler. You can just draw down in 2D these two integrals. So if we look at 0 to 9 minus x squared, we're saying pretty much y equals square root 9 minus x squared. Then we get y squared equals 9 minus x squared. And then we get x squared plus y squared equals 9, and x squared plus y squared equals 3. So pretty much that's just a circle, radius 3 along the x. This is the x, and this is the y. You can't really see, but yeah, that's the x and y, radius 3. And we should also look at this bound at the same time. This bound to determine like how much of the circle we're looking at. Like the last example, we were looking like a quarter of the circle, but this example we have to look at the bounds. So the x bound is from -3 to 3. So that means we have to look at this, the upper portion of the upper portion of the circle. So now r is going to be like the pretty much the, how can I say, the radius it goes. So yeah, so the radius is 0 to 3 because you're starting from the origin. So we get 0 to 3. Yeah, and then theta is from 0 to the angle. So our angle, since it's this portion, this should have been pi. It should just be pi. I messed up when I was writing it. So it should be 0 to pi. So pretty much the little shortcut here is that you have 0 to 9 minus r squared. You just replace the x squared and y squared with r squared, so you get 9 minus r squared. And then you just draw these two bounds for dy and dx. dy is pretty much the radius, which is 0 to 3 because it's a circle of radius 3, and then the angle is from 0 to pi because they gave us -3 to 3, so it's just top portion of it. That's a little shortcut. I don't know if that helps.